I will now prove the remarkable and profound fact that the signed area of the parallelogram built upon two vectors in the plane and the signed volume of the parallelepiped built upon three vectors in the three-dimensional space equals the determinant of the matrix, whose columns consist of the components of the vectors with respect to a Cartesian basis. And I think there is no need to explain just how central this fact is to applied mathematics, and how it goes a very long way in bringing the worlds of algebra and geometry together. First, let me remind you of what signed area and volume mean. The signed area of a parallelogram equals its conventional area in absolute value, and in order to determine the sign, you must decide on the order of the vectors. If the vectors come in the counterclockwise order, then the set is said to be positively oriented, and the area is positive. If the vectors come in the clockwise order, then the set is said to be negatively oriented, and the area is negative. For example, if we said that the vector b was first and a was second, then the shortest path from the first vector to the second is counterclockwise, and the area of this parallelogram is positive. If we said, on the other hand, that a is first and b is second, now the shortest path is clockwise, and the area is negative. And of course, you must respect the chosen order of the vectors when you're building the matrix. The components of the first vector must go into the first column of the matrix, and the components of the second vector must go into the second column. Also, the Cartesian basis itself must be a positively oriented set. So if we said that this was our basis, we must say that this vector is first and this vector is second, so that the shortest path from first to second is counterclockwise. In 3 dimensions, the signed volume of a parallelepiped equals its conventional volume in absolute value, and if you want to determine the sign, you must once again decide on the order of the vectors. Here is what you do. Okay, let's say that this vector is first, this vector is second, and this vector is third. When you look down the middle of the bundle, if the vectors appear to be in the counterclockwise direction, then the set is said to be positively oriented, and the corresponding volume is positive. If the vectors appear to be in the clockwise direction, then the set is said to be negatively oriented, and the corresponding volume is negative. Equivalently, you can use what's called the right-hand rule. What you do is, you sweep these 4 fingers of your right hand from first vector to second in the shortest direction. And if third vector appears on the same side of the plane formed by vectors 1 and 2 as your thumb, then the set is said to be positively oriented and the volume is positive. However, if third vector is on the other side of the plane, then the set is said to be negatively oriented and the volume is negative. Okay, so these are signed area and volume. And now that we understand this statement, it's time to prove it. And we will discover that the proof is much simpler and prettier than you might expect. And it is a perfect combination of algebra and geometry. And it can teach us a great deal in using algebra and geometry together. There is a reason why I left these basic properties of the determinant on the board from an earlier video. In that video, we showed that any function that satisfies these properties must be the determinant. So what we're going to do now is show that signed area and volume satisfy these properties and must therefore equal the determinant. That's our simple plan of action. And 3 out of the 4 properties, remember that the linear property is a 2 for 1, will be completely straightforward. And only one of them, the part of the linear property that deals with the sum of 2 vectors, will pose a little bit of a fun challenge. So let's start with the first property. And the question is, what physical vectors does the identity matrix whose determinant is 1, correspond to? And the answer is, of course, the vectors of the bases themselves, because this vector right here has components 1, 0. And this vector right here has components 0, 1. And what's the corresponding signed area? Well, the corresponding parallelogram is a unit square whose area is 1. So the signed area of the corresponding parallelogram is 1. And we have a match between signed areas and determinants as far as property 1 is concerned. Something very similar will happen in 3 dimensions. The 3 by 3 identity matrix still has determinant 1 and corresponds to the 3 vectors of the basis. And the corresponding parallelepiped is a 1 by 1 by 1 cube whose volume equals 1. And so the corresponding signed volume equals 1. And so we once again have a match between signed volumes and determinants as far as the first property is concerned. And now you see why it was very important to specify that the basis we're working with is a positively oriented set. Otherwise, we would not have a match. And we also see that we actually don't need a Cartesian basis. All we need is a basis such that the associated parallelogram in 2 dimensions or the associated parallelepiped in 3 dimensions has signed area or volume 1. In that case, we'll have a match between areas and volumes and the determinant, and that's all we need. Okay, that's it for the first property. Let's move on to the alternating property, which is a lot of fun to think through. In 2 dimensions, the match occurs by definition, because by definition, when we switch 2 vectors, the signed area goes from positive to negative or vice versa. For example, if B is the first vector and A is the second, the area is positive. But when we switch the order and we call A first and B second, then the signed area is negative. And that's exactly what happens to determinants. When we switch 2 columns, the determinant changes sign, just like signed area in the plane. Signed volume in 3 dimensions is a lot more fun. Let's take a look. Okay, let's first call this vector first, this vector second, and this vector third. Then this is a positively oriented set, and the volume is positive. Let us now reorder these vectors. Reordering means not moving the vectors, but changing which one's first and which one's second. So now let's call this one first and this one second. And now all of a sudden, this set points in the clockwise direction, and therefore the associated signed volume is negative. So we see that in 3 dimensions, signed volumes change sign when you reorder the vectors. And that's exactly what happens in 3 by 3 matrices when we switch 2 columns. So as far as the alternating property is concerned, we once again have a match between areas and volumes and determinants. Now let's move on to the linear property. And part of the linear property is completely obvious, and the other part is a challenge. Of course, we'll start with the part that's completely obvious, which deals with multiplying vectors by numbers. We know exactly how the determinant responds when one of its columns is multiplied by a number. The whole determinant gets multiplied by that number. What happens to signed areas and volumes? Totally straightforward. Let's take a look at this picture, and let's imagine that the vector B doubles. What's the corresponding change in the signed area? Well, if B doubles, it goes from here to here. And the corresponding parallelogram goes from this one to this one, which is double the area. And I think it's very easy to visualize that the exact same thing happens in 3 dimensions with parallelepipeds. When you stretch or shrink one and just one of the vectors by a number. And this confirms that half of linearity matches between signed areas and volumes and determinants. What's left now is the other part of linearity, that deals with the sum of two vectors. And here's what we would need to prove. We would need to prove that when we think of one of the vectors as a sum of two vectors, then the parallelogram, the signed area of the parallelogram that was built on vectors A and B, equals the sum of the signed areas of the parallelograms built on A and the red vector and built on A and the blue vector, because that would correspond to the property of the determinant, which, if we think of a column as a sum of two vectors, split into two determinants, where you have one of the vectors for that column in the first determinant and the other one of the vectors in that column in the second determinant. And so what I just described is exactly the corresponding property for signed areas. So what we're going to do next is I'll take my time and draw these parallelograms very carefully, and then we'll come back and we'll see right away that the two parallelograms add up just right. And that will prove the total match between signed areas and determinants, and we'll save proving the same property for parallelepipeds in 3 dimensions for another time. All right, I think at this point, it's become quite clear that everything has worked out just right. I would like to clarify one thing that I did. Initially, the two parallelograms of interest, this one built upon A and the red vector, and this one built upon A and the blue vector, were overlapping. So what I did was, I moved the first parallelogram, the one built upon A and the red vector, down and to the right, so that now the two parallelograms of interest are side by side. And the moment I did that, I think it became abundantly clear that the blue and the red add up precisely to the parallelogram with the yellow border built upon A and B, because they exceeded by this triangle on the bottom, and that's exactly what they lack on top. So the property holds. And if you're good at visualizing shapes in 3 dimensions, you should be able to imagine a similar diagram for parallelepipeds and make sure that the same relationship holds there as well for signed volumes. And one final note, the way we chose vectors in this picture, all of the signed areas were positive. What you should do is arrange the vectors in such a way, maybe put this one to the left of A, so that some of the signed areas are positive and some are negative, and still make sure that all of the areas add up just right. And they will. And so this completes the proof.